Welcome everybody. It's a great pleasure to introduce to Nicoletta Tardini from University di Parma. She will talk about SKT and Kähler-like metrics on complex manifolds. Thank you, Nicoletta.
Okay, thank you. And of course, I would like to thank the organizers for the kind invitation to give a talk. I would like to discuss some results obtained in collaboration with Fino and Luigi Vezzoni from the University of Torino about the study of this special class of non-Kähler Hermitian matrix on complex manifolds. That is a class of strong Kähler with torsion matrix. So actually, I will call them SKT, and the relations with some curvature symmetries. Essentially, the talk will be divided into three parts. In the first part of the talk, I will recall what SKT metrics are, and we will see some results about them. So I will give an overview about SKT metrics on complex manifolds. And then in the second part of the talk, I will focus my attention in the case when the curvature of the Bismut connection, that we will see it's an important Hermitian connection related to the SKT condition. So we will see when this connection has curvature that satisfies nice symmetries, in particular Kähler-like symmetries. And since, in fact, only-potently algebras, the existence of these matrix with these Kähler-like symmetries will force the complex structure to be abelian, so to have a particular behavior. So this will motivate the last part of the talk, essentially, when we will see how SKT matrix and abelian complex structures are related on unimodularly algebras. Okay, so let me start. So the setting is the setting of Hermitian geometry. So from now on, I will denote with X a smooth manifold of real dimension 2n that is endowed with a complex structure J. Okay, so J is an almost complex structure in the sense that it's a 1-1 tensor that squares to minus the identity, but we also ask for the integrability condition. Okay, so we really want to have a complex manifold. I will denote with G an Hermitian metric on this manifold, and with omega the associated fundamental form. Okay, so omega is just a real positive 1-1 form, and actually I will call omega itself sometimes Hermitian metric. Okay, so but I will not ask for omega to be closed. Okay, omega will not be a symplectic form, so we are not in the Kähler situation, and so for this reason, in fact, we have that maybe in Hermitian geometry, the Levi-Civita connection is not the good connection to study because it does not preserve the complex structure, okay? So we want some connection that preserve the whole Hermitian package. These connections are called Hermitian, exactly because they preserve both the complex structure and the metric. And by a result of what was shown, we actually know that on a complex manifold, actually, also in the non-integrable case, his result is true, but since we are in the integrable case, we have that there exists on a fine line of canonical Hermitian connections that are completely determined by their torsion. So in fact, the torsion really plays an important role for these Hermitian connections. And this line passes through some important connection in complex geometry. So in particular, this line of Hermitian connection passes through the Bismut connection. That is the connection I'm interested in this talk. The Bismut connection, by definition, is the unique Hermitian connection. Okay, so it preserves both the metric and the complex structure. And the torsion here is totally skew symmetric. So the torsion is a differential free form. And in fact, the torsion of the Bismut connection is, let's say, deeply related to the metric itself in this way. So actually, the torsion of the Bismut connection is nothing but the dc of omega, where dc is the conjugation of d by j, by the complex structure, and omega is the metric, okay, is the fundamental form. So since omega is a 2 form, this is indeed a 3 form, and coincides with the torsion of the Bismut connection. But in general, I mean, this form will not be closed. And an Hermitian metric is called strong Kähler with torsion. So SKT for me, if the torsion of the Bismut connection is closed. Okay, so if it satisfies this relation. So since the torsion is just dc of omega, actually I'm just asking for omega to be ddc closed, or equivalently, actually, if you prefer, I mean, using the operators del and del bar, we are just saying that omega is, indeed, it's pluriclosed. I mean, it's del bar closed. Okay, so of course, I mean, every Kähler metric is SKT because in the Kähler case, omega itself is already closed. So in particular, it will be ddc closed. So Kähler metrics are the first examples we have in mind of SKT metrics. So the point is that, of course, we want to be sure that we are really enlarging the class of Hermitian metrics. So we want to look for, you know, a bigger class of metrics that do not coincide with the Kähler metrics. So we need to find non-Kähler examples. First, let me recall this definition that is due to Goduchon. So this metric, an Hermitian metric is called Goduchon or also standard. If you take not just omega, but you take the wedge product of omega with itself and -1 times, and this is ddc closed. So, I mean, if we are in dimension 2, so if we are on a complex surface, of course, we are just saying that omega is ddc closed, so Goduchon metrics coincide exactly with SKT metrics. And the important fact here is that Goduchon metrics, by a result of Goduchon, always exist on compact complex manifolds. Actually, they exist. I mean, the result is much more interesting, the fact that they always exist in every conformal class of Hermitian metrics. And we also have, if n is greater than 1, we have uniqueness in the conformal class up to multiplication with positive constants. Okay, so the point is that Goduchon metrics always exist. So this means that on compact complex surfaces, SKT metrics always exist. Okay, so every compact complex surface carry SKT metrics. But of course, the point is that this will not be true in general, okay, in higher dimensions. So again, we need to find, we want to find non-Kähler examples. So here I listed just some results concerning SKT metrics. Of course, I mean, in the literature, you can find a lot of papers about this SKT metrics. So here, I listed just a few of them, a few results. So first, SKT metrics exist on even dimensional compact real semi-simple groups. We have applications in generalized complex geometry. And on the algebras in low dimension, we have several classifications, actually. For instance, Mazen and Swan gave a classification for solvable four-dimensional Lie algebras admitting SKT metrics. In the important case, we have classifications, for instance, in dimension 6, due to Fino, Parton, Salamon, and then this classification was actually improved by Ugarte. And it's interesting here because actually, so in the nilpotent case, in dimension 6, we have that the existence of SKT metrics does not really depend on the metric itself, but depends on the complex structure, in the sense that either all the metrics are SKT or none of the metric is SKT. Okay, but this is true just in dimension 6 in the nilpotent case. For instance, already in dimension 8, the result is false. And actually there is a classification in dimension 8 due to Arrietty Fino Vezzoni. And also in the solvable case, in any dimension, there is an interesting characterization for the existence of SKT metrics on simply connected almost abelian Lie groups due to Arroyo La Fuente. Okay, so almost abelian Lie algebras are just Lie algebras with a codimension 1 abelian ideal. And so they characterize the existence of SKT metrics, in this case, in terms of algebraic data in any dimension. Okay, and also we have other ways to construct examples. In fact, for instance, Fino and Tomassini, using an interpretation of the existence of SKT metrics in terms of currents, they proved that if you have a manifold minus a point with an SKT metric, actually there exists an SKT metric on the whole manifold. It's a sort of Miyaoka extension result for SKT metrics. And also, you can construct new examples taking blow-ups of manifolds. Okay, you take a compact complex manifold with an SKT metric, and you consider blow-up along a compact complex on manifolds, in particular on a point, if you want. Then you get a new manifold that still has SKT metrics. So if you combine these two results, okay, of Fino Tomassini, you get that in fact the existence of SKT metrics is stable for blow-ups and blow-downs in points. Okay, you can go up and down in points, but you cannot do that on submanifolds because in fact, the existence of SKT metrics is not stable under modifications. I will go back to this later, but for instance, take manifolds in class C of Fujiki, which means that they are modifications of Kähler manifolds. And Kähler manifolds, we said that they are SKT. So in particular, manifolds in class C of Fujiki are modifications of SKT manifolds, but they do not admit SKT metrics unless they are Kähler. Okay, so we cannot construct new examples using modification. Okay, and also we cannot construct new examples using deformations. Okay, so the existence of an SKT metric is not stable under small deformations of the complex structure. So for instance, you take, so what does this mean? This means that you start with your compact complex manifold with an SKT metric, and you consider small deformations of the complex structure. Well, along the deformation, you can lose the existence of SKT metrics. And I think the first example was due to Fino Tomassini on a particular complex structure on the Wasawa manifold. But also, for instance, we constructed an example on with Tomassini on S3 cross S3, also confirming again, I mean, we cannot construct new examples with deformations. And also, of course, I mean, there exists a lot of different generalization of the Kähler condition, right, in complex geometry. So for instance, I mean, we already saw SKT metrics, but there are other non-Kähler Hermitian metrics like the torsion metrics. And another important class in complex geometry is the class of balanced metrics. So balanced metrics are defined this way. So you take the n-1 power of omega again with itself, take the differential of omega n-1, and omega is called balanced if you get 0, okay? And so in fact, since this is for every Hermitian metric, okay, so this is true in general, for every Hermitian metric, if you take the differential of omega n-1, then you get theta, which is a 1 form, okay, so theta is just a 1 form, wedge omega n-1, okay, so this first equality is true for any Hermitian metric. Well, then if the metric is balanced, we are saying that this theta, this Lie form, is actually 0, okay? And why I'm talking about balanced metrics? Well, because the SKT condition is essentially complementary to the balance condition, in the sense that if you have a non-Kähler metric, that cannot be both SKT and balanced, okay? So I'm saying that, you know, sometimes different non-Kähler Hermitian metrics cannot, let's say, coexist. And if your metric is both SKT and balanced, then it must be Kähler. Actually, this can be proven directly using Hodge theory, but you can also take this formula of Alexandrov and Ivanov, and you see immediately the implication, because suppose that omega is SKT, okay? So DDC omega is 0 by definition. So the left-hand side in this equality is 0. And suppose that omega is also balanced. So we said that balance means this, so theta is 0. So this theta here is 0, this is also 0. So you are left with the omega, which must be 0, okay? So omega is scalar. But in fact, it is conjecture that this is more general than this actually, okay? Because Vezzoni conjecture that SKT and balanced metrics cannot coexist on the same manifold. So the conjecture is that if you have a compact complex manifold with an SKT metric and another metric that is balanced, then in fact, there exists a third metric that is scalar. Okay, so the conjecture holds if the metric is the same, I mean, if omega is both SKT and balanced, but it seems to be true also more in general. And so in fact, this conjecture is supported by some results. So for instance, I'm back again to these manifolds of class C of Fujiki. So we said that they are modifications of Kähler manifolds. And Chiose proved that they are SKT if and only if they're Kähler. So how this is related to the conjecture? Because by Alessandrini and Bassanelli, we know that in fact, the existence of balanced metrics is preserved by modification. So balanced metrics are defined by this relation, right? So if the metric is scalar, of course it is balanced because omega is closed, so any power of omega will be closed. Okay, so manifolds in class C of Fujiki, since are modifications of Kähler manifolds, they are in particular modifications of balanced manifolds. But by Alessandrini and Bassanelli, we know that the existence of a balanced metric is preserved for modifications. So these manifolds admit balanced metric. And here you see that they cannot be SKT unless they are Kähler, okay? And also, in fact, this conjecture is proven to be, to hold on two-step nilmanifolds with a left invariant complex structure, and also on 6-dimensional Calabi-Hausdorff manifolds with the left invariant complex structure. Okay, so these results are due to Fino Vezzoni. Okay, so this was just to give you, an overview on this class of metrics and just to see a few results. So let's go back to the Hermitian connections. Okay, so we said that in the Hermitian setting, we have all these Hermitian connections that do not coincide with the Levi-Civita connection unless the metric is scalar. Okay, because in that case, the Levi-Civita connection is preserving also the complex structure. Okay, so in the non-Kähler setting, this connection will not coincide, and so we can expect that they will behave differently. And in particular, they will behave differently also at the level of the curvature. So for instance, take the Bismut connection that we said it's the unique Hermitian connection with totally skew-symmetric torsion. So the Bismut connection does not satisfy the first Bianchi identity, okay? So that is, for instance, satisfied by the Levi-Civita connection because we do not have torsion, okay? So in fact, Ivanov and Papadopoulos proved that if you consider the cyclic sum for the curvature of the Bismut connection, you do not get 0, but you get this expression that you see, it involves the differential of the torsion. So we said the metric is SKT if the differential of the torsion is 0, okay? So this term is related to the fact that the metric is either SKT or not, okay? It's 0 if the metric is SKT. And it is also related to the parallelism of the torsion, okay? Because we have here the nabla of the torsion, okay? So it seems that the first Bianchi identity is related to the metric being SKT and parallelism of the torsion. And also, in fact, the Bismut connection does not satisfy this condition, okay? Does not satisfy the fact that it is J invariant in the first two entries, okay? It's not in general of type 1-1 in the first two entries. And for instance, this equality is satisfied if you take the curvature of the Chern connection. And in fact, I mean, if you look at this, in fact, this is also saying that if you take the Ricci form of the Bismut connection, it's not of type 1-1. It's just a 2 form, but not of type 1-1 in general, okay? Because we do not have this J invariance here. Okay, so we do not have, in general, nice symmetries, if you want, for the Bismut connection. And so this is essentially the motivation for this definition. Okay, so the Bismut connection is called Kähler-like if its curvature satisfies Kähler-like symmetries, in the sense that it satisfies the first Bianchi identity and this condition, okay, of, let's say, J invariance in the first two entries of the curvature. Okay, so in fact, this definition of being Kähler-like originally was given by Yang and Zhang in the case where you have either maybe the Chen connection or the Levi-Civita connection, but then Angelotta Lugarte Villacampa extended this definition to hold, let's say, to hold the Hermitian connection in the Goduchon line. So in particular, in the Goduchon line, we have the Bismut connection. So I would say probably this definition is due to Angelotta Lugarte Villacampa. But in the literature, you can find this condition called also Strominger-Kähler-like. For instance, I mean, if you look at the papers of Yang Zhang or Zhao Zhang, you have that they call this condition Strominger-Kähler-like because they call the Bismut connection Strominger connection, okay? All right, so we have these two conditions. And in fact, they conjecture that having these nice symmetries for the curvature implies that the metric has to satisfy some property. In particular, if they conjecture that if the Bismut is Kähler-like, then the metric is SKT. And they prove that the conjecture is true for 6-dimensional Calabi-Hausdorff manifolds with a left invariant complex structure, okay? So with Anna Fino, we thought about studying essentially how the SKT condition is related to the first Bianchi identity for the Bismut connection, of course, and the parallelism of the torsion, okay? Essentially because you see we have this relation here, this proposition, I mean, of Ivanov and Papadopoulos, saying that the Bismut connection indeed seems to be related to the SKT condition and the parallelism of the torsion, okay? So we wanted to understand how these conditions are related, also in relation to the fact that the first Bianchi identity is a part of the definition of being Kähler-like. Okay, so maybe let's skip these two results just to look at the last one. So what we proved using essentially these, let's say, intrinsic formulas that we have, we proved that if you have indeed the first Bianchi identity, actually the metric is SKT if and only if the torsion is parallel. Okay, so we have these equivalents, but you see, we are not really taking the whole definition of Kähler-like. So in fact, Zhao and Zhang with different techniques actually proved the conjecture of Angelotta Lugarte Villacampa. I mean, using different techniques, they use, they do not use these intrinsic formulas. I mean, they use, they fix local holomorphic coordinates and they play with them. But they prove that if the Bismut connection is Kähler-like, which means, again, we have nice symmetries for the curvature, if and only if the metric is SKT plus the torsion is parallel with respect to the Bismut connection. Okay, so somehow I would say that this result is suggesting that it could be interesting to study this class of metrics, okay? SKT metrics, but with the additional condition that the torsion that is totally skew symmetric is in fact parallel. Because in that case, we know that the curvature has nice symmetries, okay? All right, but in fact, in dimension 2, these metrics are already known. So let me recall first this definition of another class of non-Kähler Hermitian matrix, that is the Weismann matrix. So an Hermitian matrix is called Weismann if it is locally conformally Kähler, which means exactly that, I mean, omega is locally, it's conformal to a Kähler metric, or if you want, it means that the differential of omega in general will not be 0, okay, but it will be equal to theta wedge omega for some theta d closed one form, okay? So this means being locally conformally Kähler, and Weismann means that in addition, omega theta is not just declosed, but in fact it's parallel with respect to the Levi-Civita connection. Okay, so in particular, theta is co-closed, and that would mean that Weismann metrics are in fact examples of Goduchon metrics. All right, so we have this matrix, Weismann matrix. And it's interesting because in dimension 2, so on a surface, actually, the torsion of the Bismut connection is deeply related to this theta, this Lie form, by this formula. So, I mean, it's very easy to prove once you know the expression of the Lie form associated to the matrix. So I haven't put any details here, but it's really, it's kind of natural to prove. It's very easy to prove. And so, in fact, with Fino, we proved that if you have an Hermitian surface, not necessarily compact, okay? We never use compactness here. Then, in fact, the metric is Weismann, if and only if the metric is SKT, that we said in dimension 2 being Godushan, and the Bismut connection satisfies the first Bianchi identity, okay? So, and in particular, using the equivalence we saw before, this is equivalent to say that the metric is Bismut Kähler-like. So in fact, in dimension 2, we are not, let's say, studying a new class of metric because they coincide with Weismann metrics, okay? So, but of course, I mean, dimension 2 is very special. And in fact, in dimension 2, again, if you instead, the Bismut Kähler-like condition had two properties, right? First Bianchi identity and J invariance in the first 2 entries. So for instance, if we take the second part of the definition of Bismut Kähler-like in dimension 2, actually we get that the metric is locally conformally Kähler. Okay, so essentially we get that the Lie form must be closed, just using this J invariance here in dimension 2, okay? So all these results are essentially suggesting that every time we put nice symmetries on the curvature, we get some restrictions on the matrix, okay? All right, so let me just say something about the examples. I mean, we discussed some general results, but so let's see if we have examples of this Bismut Kähler-like matrix. So, I mean, of course, I mean, we said in dimension 2, being Kähler-like means being Weismann. So, in fact, compact complex surfaces admitting Weismann metrics are classified by Belgun. And also another trivial examples are given by Bismut flat manifolds. Okay, because if the Bismut connection is flat, the curvature is 0, so all the symmetries for the curvature are, of course, satisfied. And we said before that Angelo Talugarte Viacampa gave examples of Bismut Kähler-like manifolds in, for instance, for Calabi-Yau solved manifolds in dimension 6 with the left invariant complex structure, of course. And also with Fino, we studied this condition of being Kähler-like in any dimension for almost abelian groups. I mean, we said before that for almost abelian algebras, Arroyo Lafuente gave a characterization for the SKT condition. So similarly, we wanted to study this Bismut Kähler-like condition for almost abelian algebras. And so it's nice because in this case, you can write down explicitly, for instance, the Bismut connection, the torsion of the Bismut connection, the curvature, and so on. Okay, so it's a nice place to look for examples. But let me say that again, we cannot construct new examples using small deformations, okay? Because again, the problem is the SKT condition. I mean, you start with your compact complex manifold with a Bismut Kähler-like metric, so in particular is SKT, but then you can deform the complex structure and lose the existence of SKT metrics. So there's no hope to have in the deformation Kähler-like metrics because they have to be SKT. Okay, so even though you add the additional assumption of parallelism of the torsion, you lose the existence of SKT metrics along deformations, okay? So the property is not open, so we cannot construct new examples in this way. And also there is this result in general for the nilpotent case for the existence of Bismut Kähler-like metrics. So this result is due to Zhao and Zhang. And it's in any dimension, okay? They take let's say, two-step nilpotent Lie algebra with an SKT metric. And so they showed that the Bismut connection is Kähler-like if and only if there exists a special orthonormal basis. Okay, so for the purpose of this talk, I mean, it's not important to really look at the details of this result. I'm just interested in the last line of the theorem, okay? Because they show that in particular, the complex structure has some particular behavior, okay? So it's abelian. We are going to recall what being abelian means. So, but the point is that, so in the nilpotent case, having a Kähler-like metric is forcing the complex structure to behave in a particular way, okay, to be abelian. And so at some point with Anna, Fino, and Luigi, with Vezzoni, we were trying to study this Bismut Kähler-like condition, also in relation with the pluriclosed flow. I will not talk actually about the pluriclosed flow. It's this, but anyway, so it's this flow of Hermitian metrics that preserves the SKT condition. So we were wondering whether it preserves also the symmetries of the curvature, okay, this flow. And so,
sorry, Nicoletta.
Yeah.
Can you hear me?
Yes.
Yes. So quick question in this about this. The J has to be abelian. You also computed the Kähler-like SKTs in the almost abelian case, right?
Yes.
With Anna. So is it true that the J has to be abelian in that case as well?
I don't think so, but actually I should check. Yeah, right. So I didn't check. I would say no, but because we needed, actually we added some additional hypotheses on the let's say the algebraic data in order to study really the Kähler-like condition. But I would say that J is not abelian in general, but I should check. Thank you. So
yeah, thanks.
Okay. All right.
Nicoletta?
Yes.
Excuse me. For this Kähler-like,
yes.
Are there examples in nilpotent but not two-step?
Yeah, I don't know, because the point is that being Kähler-like would imply that the metric is SKT. And so
okay.
we have the conjecture, right? Saying
Thanks.
that if you have an nilpotent Lie algebra with an SKT metric, then it has to be two-step.
Okay, okay.
So that's why essentially they assume here at the beginning two-step, actually. Yeah. Okay, so yeah, so we were trying to study this condition along this flow, the pluriclosed flow. So we did that. Actually, I do not know the answer. I mean, I do not know whether the pluriclosed flow, for instance, not just preserves the SKT condition, but maybe preserves also this Kähler-like condition. So we proved that in some special cases, for instance, in the almost abelian case or in the for Weissman surfaces, but with additional hypotheses, actually, not even in general. So we were wondering what happens in the nilpotent case, at least because we have this result. But I mean, but you see in this result, we saw that J has to be abelian. So we were wondering how is this related to having an SKT metric? So how deeply the SKT condition is related to the abelian condition. So essentially that was, I mean, this result was really the motivation for what I'm going to say right now. So now let's recall what an abelian complex structure is, okay, in general. So take a two-dimensional Lie algebra. So an almost complex structure is called abelian if the Lie bracket is J invariant, okay? So if we have these equalities. So in particular, we see immediately that actually this is forcing the almost complex structure to be integrable, because if you take the Nicoletta tensor, I don't know, for instance, you can put J here, so this cancels with this, and then you can put J here, so you change its sign, so the two cancels, so we get 0, okay? So having an abelian, so we can just have integrable abelian complex structures. And these complex structures are called abelian because actually we have that the I eigenspace of J, so G10, is an abelian subalgebra, okay, of the complexified G, okay. I mean, you take bracket of two 1, 0 vectors. So, but then you have this J invariance, so that would give I squared, so -1, so you would get 0, okay? So this is clearly abelian, and also it's conjugate. And also we have this other important property that we can have abelian complex structures only on two-step solvable Lie algebras. Because the commutator of G, so let's say G1, okay, the commutator of G and G is abelian. So, which means that the commutator of two commutators is 0, so G is two-step solvable. Okay, so actually, okay, so later when we are going to see that under some assumption, the Lie algebra will be nilpotent, the fact that G is two-step solvable doesn't mean a priori that the nilpotency step will be 2. Okay, so actually, if I remember correctly, Barberis and Dotti have these examples in any dimension of nilpotent Lie algebras with abelian complex structures. So in particular, the Lie algebras are two-step solvable, but the nilpotency step is arbitrarily large. Okay, it doesn't have to be 2. Okay, so when we want to prove that the Lie algebra is two-step nilpotent, we not just have to prove that it's nilpotent, but we want to prove that it's also two-step. Okay, so in this setting, actually, the existence of special Hermitian metrics compatible with abelian complex structures has been studied by many authors. So for instance, in the Kähler case by Andrada Barberis Dotti, in the balance case by Andrada Villacampa, in the locally conformally Kähler case by Andrada Origlia. So actually, we already mentioned, we already recalled the definitions of these metrics. And also, in fact, Fino, Vezzoni studied the relation between abelian complex structures and Hermitian symplectic metrics. So, so let me recall briefly what Hermitian symplectic means. So you can think of this definition, let's say, in 2 ways, in a more symplectic fashion or in a more complex fashion, Hermitian fashion. So in the symplectic case, you would say that there is a symplectic structure taming J, taming the complex structure. But actually, this is equivalent to say that we have, in fact, a special SKT metric. Okay, this was proven by Fino Vezzoni. So Hermitian symplectic metric means that omega is not just Delder-Bar close. Okay, Delder-Bar close means SKT. But we have that the del of omega is Del-Bar exact. Okay, it's not just Del-Bar close, but it's Del-Bar exact. And moreover, if you take this form here, it's Del close. Okay, so this means being Hermitian symplectic. And in fact, as far as I know, there are no non-Kähler Hermitian symplectic examples, actually. So Fino, Vezzoni studied this condition of being Hermitian symplectic in relation with having an abelian complex structure, okay? And so what they proved, okay, so take the algebra with abelian complex structure and Hermitian symplectic metric. And so they proved that the algebra is in fact nilpotent. And then they conclude, okay, we cannot have an Hermitian symplectic metric on a nilpotent Lie algebra, which is non-Kähler, okay? So yeah, but the point is that, so they already studied, let's say, the relation between abelian complex structure and special SKT metrics. So the result I'm going to state right now can be thought, if you want, as a generalization of this result. Okay, because we take abelian complex structure, but arbitrary SKT metric. Okay, so yeah, so we have this, so we proved this. So take a unimodular Lie algebra with an abelian complex structure and an SKT metric. Then in fact, the Lie algebra must be two-step nilpotent. So which means, just to recall, just means that the commutator of G and G is commuting with the whole Lie algebra, okay? It's contained in the center. And so again, having two-step, even though the Lie algebra is two-step solvable, doesn't mean that the nilpotency step has to be 2 a priori. So we need to prove also the two-step nilpotency. But also let me comment this assumption, unimodularity, which means that the trace of the adjoint operator is 0. So of course, I mean, if you want to construct compact complex manifolds, so at the end of the day, so you want the algebra to be unimodular. I mean, it's a necessary assumption in that case because by Milnor, we know that if we have a simply connected Lie group with a lattice that admits a lattice, so you construct a compact quotient, then the Lie algebra must be unimodular, okay? So it's not a strong assumption in that case, in this case, but it's also necessary in the sense that if you drop the unimodularity in this result, I mean, in this theorem, this would be false. I mean, you can find Lie algebras, not unimodular, with abelian complex structure and actually Kähler metric, not just SKT, but also Kähler, that are not nilpotent, okay? So you need unimodularity in this theorem. You cannot drop it. Okay, so also let me say that actually this result, maybe not explicitly stated, but was already known in dimension 4 and 6. Again, because in low dimension we have classifications. For instance, Andrada Barberis-Dotti have classification of abelian complex structures on 6-dimensional algebras. And so you can, for instance, take this classification and study the existence of SKT metrics there and see that, in fact, you have that SKT plus abelian complex structure implies two-step nilpotent. All right, and also let me say that this result, under the additional assumption that the commutator of G is totally real, follows from a recent paper by Freibert and Swan, saying, because they study, actually in general, they study two-step solvable Lie algebras. In particular, if you have an abelian complex structure, you are in this case. And they study the SKT condition there with some additional assumptions. So, but they use different techniques. So, in fact, so with this assumption, you can find this result in their paper. Okay. But we
may I ask a question, Nicoletta?
Yeah, of course.
How wide is this space? So, two-step nilpotent with SKT metric in the abelian case.
I mean,
so are there many examples, or?
I think that in dimension 6 there are not so many examples already.
What do you know about higher dimensions?
I don't know. I'd say that it's maybe not very large, a very large class of manifolds. Yeah, but I do not know how to be more precise than that, actually. Yeah.
So are there examples in higher dimensions?
Yes, I think so. Also in dimension 8, for instance, yeah. Higher than 8, I would say, I don't know. But yeah, I think so, yeah.
Okay, thank you.
But yeah, probably I should check carefully, but I think so, yeah. Okay. Okay, so let's try to at least see the steps of the proof, okay, of this. So of course we need, so very briefly, so in fact we need to study how, essentially first, what does it mean to have an SKT metric in relation with an abelian complex structure, okay? So in fact, you can prove directly that if you have an abelian complex structure and an SKT metric, then in fact, the metric has to satisfy this expression, which in fact, I mean, a priori, the first time you see it, maybe, I mean, at least to me, didn't say much. But in fact, turns out to be very useful when you want to express how the center is. So what is the expression of the center of the Lie algebra? So let me denote with zeta the center of the Lie algebra, and with G1J, we denote this. So G1J is just the commutator of G and G plus J, the commutator of G and G. Okay, so why people usually define this? Because in general, the G1, I mean, the commutator of G and G is not J invariant. Okay, so that's why G1J turns out to be very useful, because it's a J invariant Lie subalgebra of G. not necessarily, it's not necessarily a proper subalgebra, okay? It might coincide with G, but in general it is J invariant, so you can induce the complex structure on G1J. So the idea right now would be, so suppose that you prove that G1J is a proper subalgebra of G, then you can induce on G1J the whole Hermitian structure. I mean, you can induce the complex structure and the SKT metric. And so we know that the result we want to prove, this result, is true up to dimension 6, actually. So somehow the idea would be, okay, maybe I want to use induction using G1J if I know, when I know that G1J is strictly contained in G. Okay, so that will be essentially the idea. So first, let me say this, that it's a corollary of the previous results. So again, combine abelian complex structure and SKT metric, and take the previous expression, okay, so this expression here with xjx and yjy, okay? So in fact, you get this equality. So this means that an element x in G is in the center of the Lie algebra, if and only if the commutator of xjx is 0. I mean, of course, if x is in the center, this commutator will be 0, but the point is that if you have that this is 0, you will get 0 here, so this must be 0, so x is commuting with all the elements in G, so it's an element of the center. Okay, so zeta is just the set of element x in G such that the commutator of xjx is 0. Okay, and so this was an important part of the proof. And also, so this is what we wanted, because I mean, here we do not need any condition on the, I mean, we do not need any metric actually. We have a unimodular Lie algebra with an abelian complex structure. Then what we have is that G1J is a proper subalgebra of G. And here we need the unimodularity assumption. The idea of the proof would be is to do it by contradiction, okay? Assume that G1J is equal to G, then this would mean that the Lie algebra itself can be written as an abelian ideal, because J, the complex structure is abelian, so this is abelian, plus J and the same abelian ideal. So under our assumption, using a result by Barberis and Dotti and Andrade Origlia, at the end you would get that the Lie algebra would be nilpotent. But you cannot, I mean, this is a contradiction, I mean, you cannot have the equality here for nilpotent Lie algebras. This is due to Salomon, okay? So yeah, you argue by contradiction here. And so this was the other part, essentially, of the proof. Again, I mean, we do not need unimodularity except for this moment. So again, you have abelian complex structure and SKT metric. And suppose now that G1J is two-step nilpotent, then we prove that under our assumption, the Lie algebra is two-step nilpotent. And at least, I mean, for us, it was important to understand how the center is behaving in this case. Okay, and essentially this is the induction step, okay? Because, okay, so let's see now that we have all the ingredients, what would be the proof of the theorem. So the hypotheses are unimodular Lie algebra with abelian complex structure and SKT metric. And we want to prove that the Lie algebra is two-step nilpotent. So, I mean, in low dimensions, we know it. So let's go to higher dimensions. So suppose that we know that this is true up to dimension n-1. So since the Lie algebra is unimodular and J is abelian, we know that G1J is a proper Lie subalgebra of G. Okay, so we can induce the whole Hermitian structure on G1J. Okay, so we have on G1J an abelian complex structure and SKT in the metric. So G1J is two-step nilpotent by induction assumption. And so now we use this. If G1J is two-step nilpotent, then the whole Lie algebra is two-step nilpotent. Okay. Okay, so this was essentially the idea. Let me just say, to conclude, that, I mean, we do not need unimodularity except for this moment. So again, you have abelian complex structure and SKT metric. And suppose now that G1J is two-step nilpotent, then we prove that under our assumption, the Lie algebra is two-step nilpotent. first, again, this result is supporting the conjecture of Fino and Vezzoni, saying that in the nilpotent case, okay, for an nilpotent Lie algebra, if you have an SKT metric, then the Lie algebra must be two-step nilpotent. So yeah, we already actually mentioned this conjecture earlier. So, I mean, the existence of an SKT metric is forcing the nilpotency step to be 2. I mean, in our result, and it is conjectured that this is true in general. And just to go back to the Kähler-like symmetries. So if you remember, we started with that result saying that in the nilpotent case, if you have a Bismut Kähler-like metric, then the complex structure must be abelian. So we thought, okay, so maybe actually it could be that in low dimension, when the complex structure is abelian, in the nilpotent case, maybe, you know, the Lie algebras with SKT metrics coincide with the Lie algebras with Bismut Kähler-like metrics. Maybe in that case, it's so particular that so that the two conditions coincide, but this is not the case. I mean, there exists an example. Actually, you can find it in the paper by Angelo Ugarte Villacampa of an nilpotent 6-dimensional Lie algebra with abelian complex structure and SKT metrics that do not admit any Bismut Kähler-like metric. Okay, so even though the complex structure is abelian, the two conditions being SKT and having nice symmetries for the curvature do not coincide. Okay. Yeah. So yeah, I can stop here. Thank you.
Okay, thank you very much, Nicoletta. Very nice talk.
Thank you.
Are there any other questions? Question, comment?
Nicoletta, do you think this conjecture is true?
Sorry?
Do you think the conjecture by Fino Vezzoni is true? What's your feeling?
Oh, wow. Yeah, my feeling would be yes, but yeah, I really don't know. I mean, if you can show me a counterexample, yeah, it would be very, very, very interesting actually. What this I mean, it must have some very interesting behavior if there is a counterexample actually, I would say, right? So, yeah.
Have you tried to adapt your proof for a general J?
No, actually, we really made use of the abelian complex. I mean, the abelian condition for the complex structure. No, we didn't try. Yeah.
Thanks.
Other questions? Okay, we thank again to Nicoletta for the nice talk, and the next talk will be on July 28th, because in 1 month, because in 2 weeks there is a huge conference, MCA, and the 3 organizers are involved in it. Okay, so thank you very much, Nicoletta, again.
Thank you again. Okay.
Yeah, thanks, Nicoletta. Nice talk.
Thank you. Bye, everyone.